All right, hello everyone. Welcome. What's up, David? Nice to see you. Today we'll kind of wrap up our work on discrete random variables and then start our work on continuous random variables. So just before I get started, I just want to let you guys know I am really, really close to being done with your first homework assignments. I grade one question at a time. So I've graded the first 5 questions on everyone's assignment. I just have the last question to grade. So that will be done by the end of the day, probably shortly after class. So you can check your grade on that. I'll just say things are going great. Your first assignments are looking really, really good. So thanks for that. You can check the solutions for this after the assignment is due. It gets moved down here. And if you click on a past due assignment, now you can see the solutions are posted up here if you want to check your work. And I grade your homeworks offline, and then I'm going to upload them back online. So in the comments of your assignment, you will see, I haven't uploaded them yet, but you'll see a marked up version of the homework assignment that you handed in. If you do have any questions about seeing those comments or anything like that, just let me know. And so the next homework assignment, again, is not due tomorrow. It is due on Monday at midnight. So if you do have questions on that assignment, I do have office hours tomorrow, so you're welcome to come by there with some questions. So before we get started, are there any general questions that you guys have? Okay, great. So just gonna warn you, this computer crashed this morning for a minute, so I had to move to my laptop. I'm gonna give it a second chance today, but if for some reason you lose me, I'll be right back. I'll just need to log on with another computer. Okay, so just to catch up with where we left things last time, we were doing some work with binomial distributions. We discussed geometric distributions, and we didn't quite get to, and uniform distributions, we didn't quite get to Poisson distributions. So for you all, I think it might be useful to have some sort of sheet like this handy that just kind of summarizes the main formulas, how we work with these distributions, how do we identify when we want to use these distributions. I left off the uniform distribution because that's usually a bit easier to work with. But right, we spent quite a bit of time on binomial distributions. And so over here is kind of the formula that we talked about last time for how we could calculate how likely is it that we get exactly X successes. And then we talked a little bit about how we can do these calculations in R. So I want to start today with a little bit of practice with that. So just remember, the real distinction here is really just the first letter. So we use D, and that's consistent with these other formulas to denote the probability distribution. So in other words, how likely are we to get exactly X successes, where the P is used for the cumulative distribution. So in other words, this is saying how likely are we to get at most X successes. So that's adding up a bunch of these probabilities. And these cumulative distributions we write with the capital F. The lowercase f is referring to the probability distribution. For geometric distribution, we talked about this a little bit last time. It's a very similar situation to a binomial distribution, except you no longer have a fixed number of trials. So you're repeating a bunch of trials. Each trial has 2 outcomes, and the probability of success is the same on any one outcome. But in this case, it's really just a special case of the binomial theorem. We're counting up how many failures did we get before we had the very first success. So in other words, if we wanted to know how likely are we to have X failures before our very first success. It's going to be, we need to have X failures in a row. So that's what the Q to the X means, times the very first success. So this is actually not very difficult to calculate with a regular calculator, but there are built-in functions that can do the same sort of thing. Yeah, and I also kind of included the shortcuts for the expected value and the variances. But any questions about these two distributions that we talked a little bit about last time? Okay, and then the last one that we kind of didn't quite get to is what's called a Poisson distribution. And so this is going to be used in the situation where we want to figure out how likely is it that a certain event occurs a certain number of times in a fixed period if we know on average how many times that event occurs in a fixed time period. So we'll do an example of this together, and then I'll have you guys work on some in groups. So the probability distribution looks like this. So it's a pretty messy looking formula. So I think in this case, you really would want to use R to help you calculate these. And the function is dPOIS or PPOIS. And in this one, there's going to be two things that we need to input. What is X, and then what is lambda? So we use this letter lambda, this Greek letter lambda, to denote the average number of occurrences that occur in a certain time. And the expected value and the variance are super easy to calculate here. It's just going to be lambda in both cases. And then keep in mind, if you did want to calculate the standard deviation on any of these, we get that by taking the square root of the variance. Okay, so that all is also summarized over here in the notes. So let's take a look at 12, which is going to require us to use this Poisson distribution just to make sure we know how to identify what lambda is and what X is. So here, the idea is we're told that on average, 12 cars cross a bridge. And so this is why it's a discrete random variable, because we're counting things. How many times does this occur? And we can't have like half a car. So in this case, we're saying that, okay, our fixed period of time here is each minute. And so in each minute, we have 12 cars on average. So our value for lambda here is 12. And we might describe that random variable by saying X, which is counting how many cars cross the bridge in a minute, is given by the Poisson distribution with lambda equals 12. And so this is asking me to find the probability of having 17 or more cars drive over the bridge in a minute. So in other words, what is the probability that X is bigger than or equal to 17? And there's no built-in function, though you can change the options a little bit if you want. But in R, right, the built-in functions are the cumulative and the probability distribution. So we can't quite use just P plus and then plug in 17 for X, because we want to know bigger than or equal to 17. So in order to help use one of those formulas, right, if I add up the probability that it's less than or equal to 16 plus the probability that it's greater than or equal to 17, that would be the full probability space. So we can think of X being less than 16, less than or equal to 16, as being the complement to greater than or equal to 17. And we don't need to worry about anything between 16 and 17 because X can only be integers here. So that would include everything. So here I could do 1 minus d Poisson because I want the cumulative distribution. My value for X is now 16, and the value for lambda we were told was 12. Any questions? And so just to check that calculation, I've got R open. You can do that all in one line. So I can say 1 minus, got my P. And you can see that there's like a little help box that pops up when you start to use these built-in functions that actually tells you what to enter. So the first thing would be X. The next thing is lambda. And then you have some additional options at the end that we don't need to worry about. So that gives us 0.94, etc. Questions? And so one thing that's nice, if you're thinking about how am I going to do my homework or hand in my homework, if you're typing them up, then you can just copy and paste into a Word doc or whatever you're doing. So if you don't believe me, I could just copy this over here, paste it over there, and that's fine. So when you're doing your work, if this is how you're calculating your probabilities, then I would like to see the code that you entered and the corresponding output that you get, and that's fine. If you're using the formulas, then show me that work. But I do want to see some supporting work, not just the number that you get. Any questions?
Okay. What about if we're using a calculator?
Yeah, so if you're using a calculator, then that means you're using a formula. So then you can just kind of write out the formula and then write out the calculation that you plug into your calculator.
But like if I have a computer algebra solver calculator, so it just like has the functions built in. So it's kind of like.
So the only technology that you're allowed to use in this class is either going to be R or a scientific calculator. So I think it's going to be really useful to get used to doing R because you might use that in some of your subsequent classes.
Okay.
Yeah.
I understand.
Yeah, so if you're going to use technology and built-in functions, then yeah, let's all use R because yeah, there's going to be no way of avoiding R shortly. So the more we get comfortable with it now, the better we'll be. Yeah.
I'm all for learning new coding.
Yeah, and so if anyone's interested in like actually pursuing jobs in data science when you're done, I would suspect that any employer is going to want to know what sort of programming experience do you have in data science. They're going to want you to know R and Python. I'm almost certain for a job. So some of our classes use R, some of our classes use Python. You could probably use either one to do most of these things. So I think it's good to have experience with both of them. Okay, so any other questions? Okay, so sorry, last time I did a lot of talking. So this time I would like to have you guys have an opportunity to talk with each other. So I'd like us to think about this last question, number 13. It's got 3 parts. The actual calculation in each of these parts, you guys should do in R. But I think what's going to be important in these problems is to kind of first think about right, what distribution should we use? And then let's think about how we're going to get R to do that. We can't have R do anything. R is not going to tell us what the distribution is, right? We need to read the problem and then think about, well, what's the distribution that's going to be at play? And yeah, I think one good thing to notice would be, is it discrete or is it continuous once we start to think about those? So this is discrete. And we can kind of just start this first one together. So I want to figure out, okay, what distribution is going to help me calculate this probability? Does anyone have a suggestion? You're welcome to chat it or say it. Let me just say, as far as these 3 go, right, we're thinking about discrete, binomial, Poisson, or geometric. So what do you guys think?
I would say no binomial because it's not a binary outcome.
Yep, we can get rid of that one. We're not repeating the same thing and counting up successes. It doesn't have that feel to it. That's right. Now we got 50.
I would guess geometric would be a no.
Geometric is a no, kind of for the same sort of reason, right? We're not counting successes or failures. So by a process of elimination, yeah, this is a Poisson distribution. And anytime you see this, right, where we're told, like, here's how often this occurrence happens in a certain fixed time period. Now I want to figure out how likely is that occurrence to happen in that same time period. That's a good Poisson distribution question there. That's right. Okay, so any questions about what to do before I break us up? Okay, so the rooms are open, and Yua and I will kind of be checking in to see if you guys have any questions. If you do have questions, there is a button that says, you know, I have a question, and if you click on that, then I'll know to come into your room.
Are we just doing A then?
So yeah, so 13, A, B, and C. So try all 3 parts of those. Yeah. Yeah, so let's bring it back to the probability here, which is great. Nice chatting with all of you in the discussion rooms. And yeah, it seemed like the work is going well. Let me just kind of share what came up in the rooms that I was in, and feel free if I missed something interesting that was going on in the room that you was with, just catch me up. But yeah, one thing to clarify, I don't know if this came up in the other room, but yeah, I did make a mistake here. Sorry, I had a D here and it should have been in P because we're doing a less than or equal to. So that clearly changes the probability there. Sorry about that. But as far as these go, in 13, yeah, the groups I talked with were, you know, able to identify that this was Poisson. And I think if you're having, you know, if you're thinking about what are the steps that I can do to work on these problems, it's kind of like step 1 is to think about what distribution to use. Step 2 is to maybe, you know, change the question and write it out in terms of probability. And this helps because whether you have an equal sign or an inequality, that's going to determine whether you use a D if you have exactly, or one of these inequalities would mean you're going to want to use a P in some sort of way. Good. And so were there any questions about this one in any of the other rooms? Feel free to slam the brakes on this. The part B was a D, geom. So here, this was a geometric distribution, and we were kind of talking about, it looks pretty similar to a binomial distribution. In fact, it's kind of like a special case of a binomial distribution. But what's different about this one is we're specifically looking for the outcome where we have a bunch of failures, which in this case, airbag opens before our very first success, which in this case is the airbag doesn't open. The thing to be careful about here is the fifth attempt includes that first success. So when we're working with the geometric distribution, we're only counting the first set of failures. So we would plug a 4 in here because we have 4 failures before that fifth attempt is a success. Okay, and then for this one right here, we finally have the binomial distribution where we have 25 patients calling in. We're counting up how many have the flu. So that means that's this. And since we're talking about quarantining, the one good thing is flu rates are down quite a bit this year as a result of us wearing masks and socially distancing. It's good for the flu as well. But here we're counting up how many people have the flu. So that's a 4% chance of occurring. So if we want to calculate the probability that exactly 4 happen, that's going to be we'd have a 4 and 25 and 0.04. And I kind of just added this additional question here. If I wanted to calculate the probability that X is at least 5 patients, that means that to calculate this one, we could use that sort of complement trick again by saying, well, greater than or equal to 5 is the complement of less than or equal to 4. And these less than or equal to formulas are the ones that are built in. So we could do something like that. So when you're working on your homeworks, please do include the formula that you use as well as the output. You don't have to copy and paste it. You're welcome to just write it by hand like I did here.
So why would it be P binom? If you don't mind me asking.
So we're working with the binomial distribution, and because we're initially trying to calculate the probability of greater than or equal to, so you use a D when we're trying to calculate an exact probability. What's the probability that X is exactly equal to this? In a situation when we're dealing with at least or at most, these are going to be situations where we're going to want to use a cumulative distribution. So the P stands for what this piece over here is calculating is exactly this. So the 4 is giving us the value of X. This is still telling us N. That's still telling us P. But when you put a P over here, it changes the equal sign to a less than or equal to sign.
Cool, thanks.
Yeah. Anything else? Okay, then let's take a look at some work with continuous random variables. Let me add that over here. So this is going to be worksheet for A, that's up in Canvas. Okay, here it is. Yeah, so this was basically pretty much the video being set up over here. So when we're measuring things, these are when we're going to typically have continuous random variables. So for example, if we measure the weight of a package that we're sending, it doesn't have to be 1 pound or 2 pounds. It could be 1.2, 3, 5, 6, 8, 9, 10. Well, not 0.10, but you get the point. Could be any sort of value. So when we have decimal possibilities, that's when we call this a continuous random variable. And so now our graphs are no longer like a discrete set of points, but they're going to be continuous curves. And so when we calculate probabilities with continuous random variables, we're working with areas, which means here comes the calculus that you guys had to take to get into this course. Is we're going to need to do some integration on these. So, we're not changing what we call a random variable. We're just saying that now we're no longer mapping to the integers, but we're mapping to a continuous interval of values. We're still going to use the same notation, which is lowercase f of x is going to denote the probability distribution, and capital F is going to denote the cumulative distribution. So just so like the properties that we talked about before are going to be true here, namely that this is a probability, so it has to be a value between 0 and 1. So, okay, in this case, if I wanted to write out this probability distribution, then what we could say is the probability that you have a GPA between, for x between 0 and 4, that is 0.25. And otherwise, the odds of having a GPA less than 0 or bigger than 4 is 0. But you could have a GPA that's any decimal value between those. So this is a case of what's called a uniform distribution for a continuous random variable. Okay, so this is maybe not how GPAs are typically distributed. What this is saying is that there's the same number of people that have a 0 GPA as 1, as 2, as 3, as 4. So you're equally likely to have a GPA of anything between 0 and 4. And so if we wanted to calculate the proportion that were between 3 and 3.5, this was kind of the reading quiz. We could look fancy and technically speaking, right, we would want to integrate the probability distribution from 3 to 3.5. So this tells me exactly the probability that it's between 3 and 3.5. And then, you certainly could integrate if you wanted to, but this is a rectangle, so we don't need to be too complicated here. Its area is, right, the base is 1/2, and then the height over here is 0.25. Whoops. So that would come out to 0.125. And this one was pretty much done on the videos, and you guys had something similar on the quiz. So any questions about these sorts of examples? This one over here, it is now no longer uniform. Maybe it's looking slightly normal, but not quite either. But yeah, for part A, you would want to calculate this area. And in part B, it would be all the rest. So, or no, not all of the rest. So the thing we want to be careful about here is we are reading probabilities with areas, by calculating areas. So more generally speaking, yeah, the curve might look like all sorts of different things. But again, these are the same properties that we saw for discrete random variables. First of all, this is a probability, so it has to be bigger than 0, so we're never going to have these graphs go below the x-axis. When we integrate over the entire sample space, this entire area beneath the curve should be 1. And so if we want to calculate what is the probability, that the random variable is between any two values, then that means we're going to just calculate what proportion of the total area falls between those two values. Any questions? That's kind of a quick rundown of the quiz material for today. Okay, so let's consider the following example. So here we have a continuous distribution. What we're looking at is the probability that a transistor fails. Okay, and so this is a continuous random variable because it could be 1 month, it could be 2 months, it could be 1.675 months. It could be anywhere in between. So we're thinking about X as months here. Yeah. So if we're trying to calculate, for example, the probability, well, I should say, first of all, if we want to calculate this probability, we need to figure out what this value C needs to be, right? So A is denoting the initial start, and B is denoting the end time cutoff. So if I want to figure out what the value of C is, we need to use this property that when I integrate over the entire sample space, I should get 1. So in case you're kind of curious about what the picture is here, this graph is like a decreasing exponential function. So it looks something like this. And this value of C should be so that we get exactly 1 when I integrate from 0 all the way out to infinity. So here, the sample space would be, it's possible that this transistor fails right away after 0 months, meaning it's defective from the get-go, okay? Or it's possible that it could take, 100 years for it to fail. And hopefully it makes sense in this example why the graph looks something like this. As time goes on, it's less and less likely that it's going to last that long. So the most likely thing is that this transistor fails sooner, and then as time goes on, it's less and less likely to operate for an infinite amount of time. I see. I should read my own problem. So that's one way that we could figure out what C is, by saying, okay, when I integrate over the whole probability space, I should get 1. This is also telling us that if we integrate from 0 to 6, then we should get 0.1. And so I don't want to go through all of the calculus here together. I don't think that's our the best use of time, but maybe just think about what are the equations that we would want to set up. But I'll put up the full solutions about how we would solve for C if you want to check that work at home. But does it make sense where I got either one of these equations from? Right, so this one is going to be true in general for any one. Right here, I was able to set this up because we were told this. This is probably going to be easier to work with so that we don't have to deal with an improper integral, but we could do it either way. And if I wanted to calculate what is the probability that this transistor fails in between months 6 and 12, then we would take the value of C that we find above. So we're gonna substitute in the value that you get for C, and let me just let you know that and the value that you actually get for C, I've got down there. So point being here, it's harder because we need to do calculus. We need to integrate, and we don't have formulas that we can just input into R that's going to tell us like we had with the discrete ones. So if it's been a while since you've integrated things, definitely make sure you get some practice. We're going to be looking at double integrals pretty quickly too when we start to look at joint probability distributions. So this here is telling us the probability that X is between 6 and 12. And I think it's good to have a picture of what you're calculating. And again, these definite integrals are telling us areas beneath a curve. Any questions about how we set up those integrals? You might have a question about how I evaluate them.
If you're integrating over that interval, how come the 6 and the 12 wouldn't be included? Because you're like saying it's an open, interval.
Yeah.
But if you're actually integrating that, doesn't that include?
Yeah, that's kind of what part C is going to get at right now.
Okay.
Yeah.
Okay.
Yeah. What happens when we change the inclusive to an exclusive? Yeah. So things are going to behave differently than they behaved for discrete random variables. So technically speaking, this is telling us over here, like, what's the probability it fails within the first 9 months? Okay, maybe including the 9th month. This is pretty much telling us the same thing. The only difference here is whether or not we include the 9. And so what happens with a continuous random variable which is not the case with a discrete random variable, is that the probability that random variable x is equal to 9. So in other words, the probability that this transistor fails at the exact instant we've hit month 9 is 0. And the reason why is if we were able to measure with infinite accuracy how long this transistor lasts, the odds of it failing at exactly the instant we hit month 9 is 0. It's unlikely to happen. We just didn't measure with enough precision. So with continuous distributions, the probability that we get exactly 9 that's not what I want to draw, or that, is 0, right? We have no area if our integral starts and stops at the same value. So here, the important thing is when we're reading these distributions, this value, the value on the function, doesn't really tell me much of anything. What I'm interested in is area beneath the curve. And so there's no area if we're just looking at a start and end point at the same point in time. So with continuous distributions, the point being, we don't really make a distinction about whether or not we include or exclude the endpoints because the probability of being exactly at an endpoint is 0 anyway. So in this case, we could have put this here and it wouldn't change things anyways. So this is true only for continuous random variables. Certainly, we didn't have this with discrete random variables. Any questions? Okay, so we have this similar notion for a cumulative distribution for a continuous random variable. And one thing that I didn't quite, well, I guess I did in the video, but when we're dealing with a continuous distribution, we call it a probability density function, a PDF. We had PDFs in statistics long before they were used in electronic documents. When you have a discrete random variable, we call them sometimes a probability mass function, PMF. And then for the cumulative case, we might abbreviate it with a CDF. And again, this is telling us the probability that x is, the random variable x is at most whatever the value is. So in theory, the lower limit of the integral is minus infinity. In actuality, it's like it would be the minimum value of x. So in the transistor case, we don't need to worry about negative infinity. The smallest value that x could be would be 0. Okay. So down here, so we have 3 PDFs. And over here, we have 3 different CDFs. And the reason I can determine, so why don't you guys tell me, like, how can you tell that this column over here is the CDF and this column over here can't be CDFs?
They're decreasing.
Yeah, that's right. So cumulative distribution functions have to be non-decreasing. They might flatten out at points, that's okay, but they can't go down. And in fact, all of these functions are going to flatten out and approach one. right? A limit as x goes to infinity should be 1 in all of these cases, because this is telling us what is the probability that the random variable x is less than or equal to its maximum value. That should be 100%. So I'd like to think about how we can match up these cumulative distribution functions with a PDF. So they're not lined up in the right way. So here we go. This is what I want to open.
All the PDF ones, their high point would be approaching 1, 2, right?
Not necessarily, right? So just to quickly scan back, right? These don't. What should be true about these functions is not that the maximum value is 1, but that the total area is equal to 1.
Great, thank you.
Yeah. So I just opened a poll, and this poll has 3 questions. So yeah, and it's anonymous, so I'm not going to know who says what. Just kind of curious how you think these graphs would match up. So question 1 is saying, which of the graphs does A match, and 1, 2, or 3, and so on. Sorry, this is helpful. All right, so take another 10 seconds to get your answers in. Okay, thanks. Well, how about that? We have uniformity here in our responses. So everybody said the same thing. That takes away from the fun of arguing about this. So let's see if you all are correct or not. So for A, you said this matched graph 2. And does someone want to just share the thinking there?
I picked that one because there's a change in concavity on the CDF, and there's a critical point on the PDF.
Yeah, so that's a really good observation here, is that there's this connection between critical points on one graph and inflection points on the other, because the relation here is so the probability distribution is actually the derivative of the cumulative distribution, or if you want to think about it the other way, you can think about it as the cumulative distribution is the antiderivative of the probability distribution. So one way that you can imagine this is exactly right. We have a critical point on this function. So that's going to correspond to points where this slope is basically 0, right? Since this is saying over here, the derivative is, I mean, maybe it's a corner, right? But at least over here, you can see that the derivative seems to, we have a critical point over here. So that's going to correspond to a point over here where the graph is flat and changing concavity as well. That's right. So we have 2 of those. We kind of have these 2 values. So what this graph is actually plotting is it's keeping track of how much area is underneath this graph. So at first we go up here And this is like the area of the first triangle. So that might be about here. And then we hit this inflection point, and then it's flat over this interval. So that's what's going on over here. And then suddenly we add some more area when we get past that point, and that's why it starts to go up again. Yep, and this one over here, right? B, you guys said matched up with graph 1. And over here, we have this one critical point, which is corresponding to that inflection point over here. So at first, the area goes up really quickly. So that's why this function is really steep. And then the area is going up by less and less and less. And that's why that graph starts to flatten out. Yeah, and so this one over here, that leaves C to match that one. So this function over here matches up with its antiderivative over there. Okay, any questions about that one? Okay, so I think this is a good place to stop. So I think the plan will be the reading quiz for Monday's class. We'll I'll kind of go through this in a video and probably ask you something similar to this. So I'll make a video where I kind of wrap up this and then ask you some similar questions that are going to really focus on finding how we find the expected value of a continuous random variable. And then we'll pick up and working more with continuous random variables. In particular, we'll be working a lot with normal distributions. That's the most common continuous random variable, and normal distributions are the kind of backbone of statistical inference. So that's a good distribution to get comfortable with. Okay, so homework again is not due tomorrow. It's due on Monday. If you do have some questions about it, I've got office hours tomorrow, so you're welcome to come by with those. And I'll get your graded homeworks will be up by the end of today. So just keep an eye out for that. Cool. Otherwise, have a nice weekend, everyone, and I'll see you all on Monday.
Thank you.
Take care.
Thank you.